Hello, welcome to Fundamentals of Acoustics. Today is the 4th day of this 10th week of this course, and what we plan to do today is introduce discrete Fourier transform, which is commonly abbreviated as DFT. But before I do that, I just very quickly wanted to mention, which I forgot to mention in one of the last two classes, is that we had said that there are two types of Fourier transforms. One is the forward transform and the other one is the reverse transform. And I had given you all the relation for the forward transform, but I missed on providing you with the relation on reverse transform. So, in next 4-5 minutes I will just discuss that and then we will move on. So, Fourier transforms So, if I have to convert time domain data into frequency domain, then I use forward transform. So, I say f of omega equals 1 over square root of 2 pi minus infinity to positive infinity f t e to the power of minus I omega t dt. So, that is my forward transform. Okay. And the inverse transform is, so what does the other transform do? If I have frequency domain data, then from that information I can get back to my time domain, and that I can do using this relation. And here instead of f t I have f of omega, capital F of omega, and instead of exponent to the power of minus omega t I have e to the power of plus I omega t, and I integrate with respect to omega. So, this is my inverse transform. So, these are important relations, and using these you can convert any continuous or piecewise continuous signal, if it is in time domain, into frequency domain, and back and forth and vice versa. Okay. So, the only condition is that the signal has to be piecewise continuous, integrable signal. It also should be integrable. So, what does that mean? That its integral over the entire domain should not become infinite, it should be a finite number. So, now next we will talk about discrete Fourier transform. Discrete Fourier transform, lot of times it is abbreviated as DFT. So, first let us talk about the need. Why do we need discrete Fourier transform? So, consider a loudspeaker and it is emitting some sound, and let us say I have a microphone here. Okay. So, that is my microphone, and this microphone is recording the signal, and the signal, it goes through a data acquisition system. So, I call it DAC, data acquisition system, and then from here my data goes into a computer, and this is a digital computer. So, the signal which is coming from the speaker to the microphone, it is a continuous signal. So, this signal is continuous, but what does the data and the signal which is coming out. So, okay, so which is entering the microphone and which is leaving the microphone, it is a continuous signal. But most of the modern data acquisition systems and the digital computer in combine, what they do is that they do not capture continuous signal, rather they capture data at every small intervals of time. So, the computer does not capture this blue curve, rather it computes, rather what does it do? It computes or not computes, it measures the value of the signal at discrete intervals of time. So, this is my time axis. So, let us say it measures every 1/10 of a second. So, I will get a lot of points. Okay. And what I will not have is a continuous curve. So, Ft is not known, rather what we know is what rather we know. So, we do not know Ft as a continuous function, rather what we know is this table. So, t at t1, t2, t3, t4 at different intervals points of time, I know the value of Ft. So, f1, so ft1, ft2, ft3 and so on and so forth. So, I do not know the continuous function, I just know points at different intervals of time after every fixed interval of time. So, if I have to do a Fourier transform for just points, I cannot do it, because my Fourier transform expression is what? My Fourier transform says that f omega equals 1 over square root of 2 pi integral of from minus infinity to plus infinity f t e minus I omega t dt. So, here I have to know f t as a continuous function, but most of the times when we get data, it is not continuous data, it is just discrete points. So, I cannot use this relation, not usable in experiments. I will not say in all experiments, but in most experiments I cannot use this formula. So, I cannot convert this frequency domain data, which is made up of points, into this time domain data, which is made up of individual points, into frequency domain. So, for that we have to learn a technique called discrete Fourier transform, discrete Fourier transform. So, what we will do is we will not go around and try to prove the relations for discrete Fourier transform, but we will just state the results. I will first write down the relation and then explain it. So, the forward transform, which converts digitized or discrete data in time domain into frequency domain, I can express it as capital X subscript k equals summation from n is equal to 0 to n minus 1 x n e to the power of minus I 2 pi k n divided by capital N. Okay. So, we will explain this formula. So, what is x n? X n, they correspond to n data points in time domain. Okay. So, what will their values be? Their values will be x1, x2, x3 and so on and so forth. But we do not start from x1 because in this formula n starts from 0. So, the first point we call it as x0, okay. And if there are n points we go up to x to the to n minus 1, okay. So, we start from 0 and we end up at n minus 1. So, xn are n data points in time domain. So, in the discrete Fourier transform, and this is the forward transform relation. So, this converts time domain into frequency domain. It converts time domain data into frequency domain data. So, this is our raw input data. So, if I know n points in time, I can use those n points to compute frequency domain data. What is xk? Okay. So, there is a error here, it should not be lowercase n, but this is uppercase n because the total number of points is n. So, this small n is just an index. So, before I talk about xk, n is the index for time, it is the index for time. So, n is equal to 0 means t0, n is equal to 1 means t1, n is equal to 2 means t2 and so on and so forth. Okay. So, finally, we get n equals n subscript n minus 1, it means t n minus 1. So, again there are n points. So, this is an index for time. Now, let us look at xk. So, what is xk? Amplitude of signal at kth frequency. Okay. And k is equal to 0 means first frequency, k is equal to 1 means second frequency, and we go up to k equals n minus 1 means nth frequency. Okay. So, k does not equal frequency, but it tells k is equal to 0 means first frequency, k is equal to it by itself, it does not necessarily mean frequency, but it tells that okay, the amplitude of the first frequency is x1, amplitude of the second frequency is actually amplitude of the first frequency is x0, amplitude of the second frequency is x1, amplitude of the third frequency is x2 and so on and so forth. So, k is the index on frequencies, it is the index on frequencies. So, n is the index for time, k is the index on frequencies. So, what does this relation show? So, if I have n data points in time, I will get n frequency components. I will get n frequency components. This is important to understand. Components. If I have n points in time, from that information I can extract n frequency components. Now, all of them may not be unique, some of them may be repeated, but we will get n different frequency components. So, what we do is, so how do we use this formula? The way we do it is, what we do is, we first get all the values of x, right, and then we multiply x0 to e to the power of minus I 2 pi k times 0 divided by n, add it to x1 times e to the power of minus 2 pi k times 1 divided by n, and so on and so forth. So, initially I set k to be 0 and I find the summation of this entire expression, then I get x0, then I change my k to 1 and I do this entire operation again for n points. So, I make n summations, so I get x1, then I go to k is equal to 2. So, initially I calculate this coefficient x for 0th frequency or for first frequency when k is equal to 0, then for second frequency k is equal to 1, and so on and so forth. So, in this way, step by step I calculate x0, x1, x2, x3 till xn minus 1, and I get for n different frequencies these coefficients x's, and then from that, so last thing, xk is, so it can be complex. Okay. So, magnitude of xk will help us. So, again xk is not same as magnitude, it will give us an idea of magnitude. Exact magnitude will tell what it means. Xk, its modulus will help us calculate what? Amplitude of kth frequency, and phase of xk will help us calculate phase of kth frequency. Okay. So, what we will do is we will now do an example, so that things become clearer. So, let us consider the relation xt to sine 2 pi ft, and let us say f equals 1 hertz. Let us say f equals 1 hertz. So, if I plot it, my signal will look like this. And these are the points. So, my experimental setup is giving me some points. So, I am going to set up the problem today and then we will continue this discussion tomorrow. Okay. So, the way I am, so f is, frequency is 1 hertz, and what my data acquisition system is doing is that in each second it is acquiring 8 sample points. So, each second I get 8 data points. So, this is my time axis, this is my amplitude. So, this maximum value is 2, and this is, how much is this duration? T is equal to 1 second. So, in each second it is getting 8 data points. So, let us count. So, and it is finding data points after equal intervals of time. So, it is not that So, these are the data points. So, my data acquisition system is not giving me the green curve, it is just giving these data points, okay, and in 1 second it is giving me 8 data points. So, let us just count these number of points. So, this is point number 1, 2, 3, 4, 5, 6, 7 and 8, okay. In 1 second I am getting 8 data points. So, I am not picking up the 9th point, because at the 9th point the cycle is going to be complete, okay. So, I am just getting 8, then in the next cycle I get 9, 10, 11, 12, 13, 14, 15, 16. So, in 2 seconds I get 16 data points, then what is it 17, 18, 19, 20, 21, 22, 23 and 24. So, in 3 seconds, so I am, let us say my data acquisition system is acquiring data for 3 seconds. So, in 3 seconds I get 24 data points, which means that n is equal to 24. So, I am having 24 data points, and using these 24 data points, how many frequencies, frequency amplitudes I will be able to compute? 24. So, n is going from 0 to 23, and the index on frequency is also going from 0 to 23. So, in the next class we will learn how to use this relation which we have shown in practical way. So, that concludes our discussion for today, and we will meet once again tomorrow. Thank you.